Let us know about composition of functions and invertible functions. Let a function f be defined from set A to set B and a function g be defined from set B to set C. Then the composition of f and g denoted by gof, where gof is defined from set A to set C given by gof of x is equal to g of fx. This can be shown graphically in this manner. Text. Let B be the subset of N, be the set of all roll numbers, and C the subset of N be the set of all code numbers. This gives rise to two functions, f defined from A to B and g defined from B to C, where fa is equal to the roll number assigned to the student A and gb is equal to the code number assigned to the roll number B. In this process, each student is assigned a roll number through the functions f and each roll number is assigned a code number through the function g. Thus, by the combination of these two functions, each student is eventually attached a code number. Let us have an example. Let f be defined from 2, 3, 4, 5 to 3, 4, 5, 9 and g be defined from 3, 4, 5, 9 to 7, 11, 15. Be functions defined as f of 2 is equal to 3, f of 3 is equal to 4, f of 4 is equal to f of 5 is equal to 5 and g of 3 is equal to g of 4 is equal to 7 and g of 5 is equal to g of 9 is equal to 11. Find gof. Let us have the solution. Gof of 2 can be written as g of f2. From the given information, f of 2 is equal to 3. This implies g of f2 is equal to g of 3. From the given information, g of 3 is equal to 7. Hence, gof of 2 is equal to 7. Similarly, gof of 3 is equal to 7, gof of 4 is equal to 11 and gof of 5 is equal to 11. Let us have an example. Find gof and fog. If f be a function defined from R to R and g be a function defined from R to R are given by fx is equal to cos x and gx is equal to 3x square, show that gof is not equal to fog, where R is the set of all real numbers. Let us have the solution. Gof of x can be written as g of fx. From the given information, fx is equal to cos x. Hence, g of fx is equal to g of cos x. Now, on substituting cos x in place of x in gx, we get gof of x is equal to 3 of cos square x. Similarly, fog of x can be written as f of gx. From the given information, gx is equal to 3x square. So, f of gx is equal to f of 3x square. Now, on substituting 3x square in place of x in the function fx, we get fog of x is equal to cos of 3x square. Note that 3 cos square x is not equal to cos of 3x square for x is equal to 0. Hence, gof is not equal to fog. A function f defined from set x to set y is defined to be invertible if there exists a function g defined from set y to set x such that gof is equal to ix and fog is equal to iy. Note that ix and iy are the functions of x and y respectively. The function g is called the inverse of f and is denoted by f inverse. Let us have an example. Let f be a function defined from set n to set y, where f is equal to 4x plus 3, where set y consists of elements y belonging to set n, where n is the set of all natural numbers, such that y equals 4x plus 3 for some x belonging to n. Show that f is invertible. Find the inverse. Let us have the solution. Consider an arbitrary element y of set y. From the above information, we can say that y equals 4x plus 3. This implies y minus 3 is equal to 4x. This implies x is equal to y minus 3 by 4. We define a function g from set y to set n such that gy is equal to y minus 3 by 4. Now, we know that gof of x is equal to g of fx. From the above information, fx equals 4x plus 3. This implies g of fx equals g of 4x plus 3. Now, on substituting 4x plus 3 in place of x in gx, we get g of 4x plus 3 equaling 4x plus 3 minus 3 by 4, which equals x. Similarly, fog of y is equal to y. This shows that gof is equal to ix and fog is equal to iy, which implies that f is invertible and g is the inverse of f. Let us have some theorems over composition of functions and invertible functions. Theorem 1. If f be defined from set x to set y, g be defined from set y to set z, and h be defined from set z to set s are functions, then h of gof will be equal to hog of f. Let us have the proof. H of gof x can be written as h of g of fx for every x in set x. Similarly, hog of fx can be written as h of g of fx for every x in set x. Hence, h of gof will be equal to hog of f. Theorem 2. Let f be defined from set x to set y. G be defined from set y to set z be two invertible functions. Then GOF is also invertible with GOF inverse is equal to F inverse or G inverse. Let us have the proof. To show that GOF is invertible with GOF inverse is equal to F inverse or G inverse, it is enough to show that F inverse or G inverse of GOF equals Ix and GOF of F inverse or G inverse is equal to Iz, where Ix and Iz are the functions of x and z respectively. On considering H equals F inverse or G inverse, we can say that H of GOF equals Hog of F. This implies F inverse or G inverse of GOF equals F inverse or G inverse of G of F. By theorem 1, on combining G with G inverse, F inverse or G inverse of G of F equals F inverse of G inverse or G of F. Now, by definition of G inverse, F inverse of G inverse or G of F equals F inverse of Iy of F. Now, by theorem 1 and the definition of F inverse, we can say that F inverse or Iy of F equals Ix. Similarly, it can be shown that GOF of F inverse or G inverse equals Iz. Let us have an example over composition of functions and invertible functions. Show that if f is defined from set A to set B and g is defined from set B to set C are 1, 1, then GOF defined from A to C is also 1, 1. Let us have the solution. Suppose GOF x1 is equal to GOF x2. This implies g of fx1 equals g of fx2. This implies fx1 equals to fx2 as g is 1, 1. This implies x1 equals x2 as f is 1, 1. Hence, GOF is 1, 1. Let us have another example. Show that if f is defined from set A to set B and g is defined from set B to set C are onto, then GOF defined from set A to set C is also onto. Let us have the solution. Given an arbitrary element z belonging to C, there exists a pre-image y of z under G such that gy equals z since G is onto. Further, for y belonging to B, there exists an element x in A with fx is equal to y since f is onto. Therefore, GOF x equals g of fx equals g of y equals z, showing that GOF is onto. Let us learn about binary operation.